All right, so now that we know our annihilators, we can start using them to help solve differential equations. So we're going to use this undetermined coefficients approach using annihilators. So let's suppose that we have this differential equation. It's not a homogeneous differential equation. So we can make the left side essentially look like a linear operator, and the right side is just this g of x function. Since it's not homogeneous, it's not equal to 0, it's equal to this function. But it still has constant coefficients. Okay, so the left side, this linear operator notation side, is still got constant coefficients. But g of x consists of finite sums and products of functions that we can annihilate. Okay, so g of x is essentially something we can annihilate. So it's, a constant or a power function times an exponential, or a power function times an exponential times a cosine, power function times exponential times sine, or just an exponential, or just a cosine, etc. And so we know the annihilators are, d to the n, d minus alpha to the n, and this d squared minus 2 alpha d plus alpha squared plus beta squared all to the n. These are our annihilators that'll work with these different functions. This is what we learned already. All right, so the idea basically goes like this. If L1 will annihilate g of x, okay, then what we're going to do is we're going to take the original differential equation, and we're going to apply that annihilator to both sides of that equation, thus making the right side 0. And so what we have is this now homogeneous differential equation that we can work with. It's a higher order equation than the original because of the L1, but it is homogeneous now. So what we're going to do is we're going to use that to help us find the form of our particular solution y sub p. Because remember, what we learned in the beginning of this unit was that when we solve the homogeneous solution, we get our general solution, and we're going to call that y sub c. But when we solve the non-homogeneous, there are two parts to the answer. There's the y sub c piece, and then there's a y sub p piece. Y sub c is the general solution to the homogeneous differential equation, and y sub p is a particular solution to the non-homogeneous. And the idea of solving this new higher order homogeneous will help us find the form of the particular solution to the original non-homogeneous. And once we understand what the form of the y sub p should be, then the next thing is to actually figure out y sub p, and that is through this method of undetermined coefficients. So that's generally the setup for how this is going to get done. And again, we use this y sub c plus y sub p, where c was the general solution to the associated homogeneous, so say L of y equals 0, and y sub p is a particular solution to the non-homogeneous. So these are the steps that we're going to end up going through to get all this done. Again, the original differential equation has to have constant coefficients in it. The annihilator approach will only work in a constant coefficient linear differential equation. And we use this for obviously the non-homogeneous ones, because we already know how to solve the constant coefficient homogeneous ones. So what we want to do is we want to first find the complementary or general solution to the associated homogeneous. So we take the original differential equation, just set it equal to 0, solve it. Since it's got constant coefficients, we've already learned how to do that. That'll give us y sub c. That's half of the answer that we're looking for. Then next thing we're going to do is we're going to apply the differential operator L1 that annihilates g of x. So you got to be able to do that. If you can't find an annihilator for g of x, this doesn't work. So we apply it to both sides, and we're going to get this new homogeneous differential equation, which we're going to then solve. We're going to solve and find the general solution to this new higher order homogeneous. Once we have that, what we're going to do is then, here's the key, delete the solutions from step 3 that we found already in step 1. Okay? Everything we found for y sub c in step 1 needs to be deleted from the solutions to this. What's left will essentially form a linear combination to tell us what y sub p should look like. Once we do that, the next thing is to actually find what y sub p should equal. So we say, well, if it's a particular solution, it should be able to satisfy the differential equation. So let's substitute it into the original differential equation. We match up coefficients of various functions on either side using what I call the equal parts method. It's very similar to something you would have seen back in partial fraction decomposition. And then we form our final solution. Once we figure out what y sub p is, we form our final solution by taking y sub c plus y sub p and say that is the general solution to the non-homogeneous differential equation. The best thing is to see all this in action as we go through an example. Ultimately, I mean, we could boil this down to, is there two steps? First step, find y sub c. Second step, find y sub p. Well, actually, you say third step, form the solution y sub c plus y sub p. The trick is, how do we do this? How do we find y sub p? And this is one way to do it. We will have another way to do it, something called variation of parameters, because annihilator approach will only work in very specific circumstances. Only if the differential equation has constant coefficients, and only if g of x can be annihilated. Other than that, you will not be allowed to use annihilators. It just won't work. So here we go. Notice we have a couple things going on here. It's a linear differential equation. It's got constant coefficients 1, 3, 2, and it's non-homogeneous, but the function it's equal to is definitely able to be annihilated with d3, third derivative. Okay? So what am I going to do? First, I'm going to find y sub c, which is to solve the associated homogeneous, which would be y double prime plus 3y prime plus 2y equals 0. So that's just a homogeneous and its constant coefficients. I create my auxiliary, which is m squared plus 3m plus 2 equals 0. I can factor that as m plus 1, m plus 2, which would give me m equals -1 and -2. Two distinct real solutions. So y sub c, because this is the solution to the associated homogeneous, y sub c would be c1 e to the -x plus c2 e to the -2x. Okay, that's the first piece. Next, we already know what the annihilator for this function is, third derivative. So what I'm going to do in my next step is I really want to just say we're going to find y sub p. Now we're going to do it using annihilators. So first thing I like to do is I like to write the original differential equation in operator notation. There's not really a reason for this, but I like to do it so it's all in the same notation. So that would be d squared plus 3d plus 2 of y equals 4x squared. That's the same as the original differential equation. Then I'm going to apply this annihilator to both sides. And what that does is it makes the right side 0. So we still have d squared plus 3d plus 2y on this side. Get rid of that. All right. Now what you're going to do is you're going to say, well, I'm going to solve what's here. It's this equals 0. I like to now go back to my prime notation. So y triple prime times y double prime plus 3y prime plus 2y equals 0. This is exactly what I'm trying to solve. It's a constant coefficient equation still, but it's a homogeneous one. And it's a constant coefficient equation. This is the reason why it's important that the original one is constant coefficients, because the annihilators all have constant coefficients. So this just creates a bigger constant coefficient equation. Well, if it's a constant coefficient homogeneous, what do? Auxiliary equation for this. What's the auxiliary equation for this one? Well, that would be m cubed times m squared plus 3m plus 2 equals 0, which we know we can factor as m cubed times m plus 1, m plus 2 equals 0. And so we get m equals 0 but this is repeated 3 times. We get m equals -1 and m equals -2. So think of this as a whole new equation and a whole new set of solutions. And how would we deal with this if this was our homogeneous? Well, we would say that the solution should be c1 e to the -x using that, plus c2 e to the -2x using that. And I like to use the ones that I've already used up here, the repetition. Then I go on to the new stuff. Well, this is the new stuff, right? So it's a solution of 0. So that would be c3 e to the 0x, okay? But then it's repeated, so then c4x e to the 0x, and then c5x squared e to the 0x, because it's repeated 3 times. 1, 2, 3. Well, e to the 0x is just 1, so technically this is a 1, this is a 1, this is a 1. But the key here is what I do is take what I already know, which is all this, and I get rid of it. And what's left over, that's my y sub p. So what this just told me is that y sub p should look like this. c3 times 1 plus c4 times x times 1 plus c5 times x squared times 1. So this is the form of y sub p. But I say the form of y sub p, and I don't say that that is what y sub p is, because y sub p is what we call a particular solution. And a particular solution needs to be free of arbitrary parameters, which are these C3, C4, and C5. So what you should do here now is you need to figure out what these parameters need to equal in order for this to be a particular solution. So I need to find C3, C4, C5. So that's why this is only the form of the particular solution and not the actual particular solution. So the undetermined coefficients are C3, C4, C5 that we need to now solve. So that's why they call this undetermined coefficients. And once we find the value of those for which this will be a solution to the differential equation, we combine y sub c and y sub p and we get our full solution. So now we got to do that. Well, how do we do that? Well, the idea is this is a particular solution. And if it's a particular solution, keyword solution, is that this should be able to plug into the original differential equation and solve it. Well, that means I need to take y sub p, and that's my y. Then I need to find y sub p prime and plug that in, and then y sub p double prime, I have to plug that in, and I have to make this side equal 4x squared. And what C3, C4, C5 will make that happen is what we're looking for. So we have our y sub p to be c3 plus c4x plus c5x squared. Okay. So then we need to say y sub p prime would be c4 plus 2c5x, and y sub p double prime would be 2c5. Okay. We're going to plug that into the original differential equation, which was y double prime plus 3y prime plus 2y equals 4x squared. And so that would give me y double prime. So this is going to go there. So we got 2c5 plus 3 times y prime. So this is going to go here. So c4 plus 2c5x. And then plus 2 times y. So all this goes here. So c3 plus c4x plus c5x squared equals 4x squared. And so we distribute this, distribute all this, and what do we get? We get 2c5 plus 3c4 plus 6c5x plus 2c3 plus 2c4x plus 2c5x squared equals 4x squared. And then we use this equal parts concept. Well, the idea is this is an equation. So this side has to equal this side. So if I take all my x squareds from the left-hand side, and there's only one of them, which is 2c5 times x squared, that has to be equal to the x squared on the other side. Well, that's 4x squared. Well, if that's the case, then 2c5 has to equal 4. And I do the same thing with the x to the first. Here's an x to the first term. Here's an x to the first term. If I put them together, it's 6c5 plus 2c4 x. There are no x's over here, so all this has to go away, which means that whole thing has to equal 0. And finally, all the constants, which is all this other stuff. So that's 2c5 plus 3c4 plus 2c3, all that has to equal 0. Because again, there's no constant over on the right-hand side. And so then we use that to find those coefficients. So in this case, if 2c5 has to equal 4, then c5 has to equal 2. And if c5 equals 2, then this tells me that 12 plus 2c4 has to equal 0. So c4 equals negative 6. And if that's the case, then this tells me that 4 plus negative 18 plus 2c3 has to equal 0. So therefore c3 equals what? So this will be negative 14, so this will be 7. And so now I know what those values would have to be. In order for this y sub p to solve the differential equation, in order for this to solve this, this is what c3, 4, and 5 would have to be. So that tells me that y sub p would actually equal 7 minus 6x plus 2x squared. Okay? Now that we have our y sub p, the next thing we want to do is form our final answer. So the general solution should be y sub c plus y sub p to the original non-homogeneous differential equation. In our case, that would be c1 e to the negative x plus c2 e to the negative 2x plus 7 minus 6x plus 2x squared. And that whole thing right there is the solution. Y equals, y equals this is the solution to the original non-homogeneous differential equation. This is called the annihilator method in undetermined coefficients. One thing you'll see done, and it's silly, but you'll see done, is they'll change the y sub p to be a, b, and c instead of c3, 4, and 5. Some people like to look at it that way. Like I said, this is very akin to what you did in partial fraction decomposition when you were trying to find the coefficients. And you could have used A, B, C then, or you could use subscript A1, A2, A3. Either way, it doesn't really matter. They're standing for some numbers that we need to find. So whether you call them A, B, and C, or C3, C4, C5, it doesn't matter. I like the subscript notation. The book and a lot of books like to use the different capital letters. You do what you want. All right, so this one, if you look at it, we got everything we need for this annihilator approach. This is linear with constant coefficients on the left. It's non-homogeneous, and the function on the right-hand side, we definitely can annihilate it. Thinking about annihilating that function, d minus 3 times d squared plus 1 would annihilate that whole function because d minus 3 annihilates the exponential, d squared plus 1 annihilates the sign, and the product of the two would annihilate the whole thing. And so first step, find y sub c. All right, so that's easy. So we get y double prime minus 3y prime equals 0. Solve the associated homogeneous. Since it's linear with constant coefficients, we do our auxiliary, which is m squared minus 3m equals 0. Factor out an m, you get m minus 3 equals 0. So m equals 0 and m equals 3. Giving me that y sub c equals c sub 1 e to the 0x, so that'll just be 1, plus c sub 2 e to the 3x. So there's your y sub c. All right, second step, find y sub p. And we're going to do it using this annihilator approach. Since we already know what the annihilator is, I'll apply it to both sides of the equation. So I get d minus 3 times d squared plus 1. This equation turns into d squared minus 3d, and the right-hand side annihilates to 0. All right. Now off of this, we would then see that this is a new differential equation. It's in operator notation. I could go back to prime notation if you wanted to. I could write this as, say, y prime minus 3y times y double prime minus y times y double prime minus 3y prime equals 0. I don't know that that's necessary. What really is important to realize, this is a constant coefficient equation, and that our auxiliary equation, since it's homogeneous, would end up being m minus 3 times m squared plus 1 times m squared minus 3m equals 0. In which case, if we factor it all out, we have m squared plus 1. We have the m minus 3, but remember this has another m minus 3, so we actually get m minus 3 squared, and then we have an m. And so what do we get here? We're going to get m equals plus or minus I out of the m squared plus 1. We get m equals 3, but that's repeated twice, and then we get m equals 0. So if we go to build our solution off of that, our y sub p, or sorry, our solution, let's not jump the gun here, our solution would be, well, if these are all the roots of this new differential equation, we would have c sub 1 e to the 0x if I use that one, plus c sub 2 e to the 3x if I use one of these. But since it's repeated, now I have c sub 3 x e to the 3x. And then I have these complex conjugates where, in this case, alpha is 0 and beta is 1. So that would give me c sub 4 cosine x plus c sub 5 sine x. Because beta is 1, so beta x would be 1x. And so looking at this, we already know that this is y sub c, so then the leftover piece here should be y sub p. And so what a lot of people ask all the time, after we do, say, the first example, is they say, well, if you're going to pull this out of the next step, right? So we go to, say, y sub p, and we know we're going to be pulling those solutions out already. Well, shouldn't just the thing that you added in there, the annihilators that you added in there, be the pieces that create, essentially, your y sub p piece? And the answer is yes, kind of. But I can't ignore what I had there originally, which is going to give these solutions because of this scenario. Because if I only looked at the annihilator part, and I looked at those factors from the annihilator, which are here, I would get an m minus 3, which would give me 3, and I had m squared plus 1, which would give me plus or minus I. But I wouldn't realize that this is a repeated real if I ignored what was already there. And so the fact that it's repeated is important because that makes a difference right here. So what you want to do is you want to realize what the process is. Realize that y sub p is largely coming from the annihilators. But if any of those annihilators share a 0 with one you already found, that's going to make a difference in your y sub p. All right. So now that you have y sub p, in order for this to actually be y sub p, we need to solve for C3, C4, and C5. And once we solve for C3, C4, and C5, then we can fully create our solution to this non-homogeneous equation. All right, so our y sub p, we said, has the form of C3 x e to the 3x plus C4 cosine x plus C5 sine x. And so we're going to need to find the derivative and the second derivative of y sub p, so we can plug it into the original differential equation to get the values of C3, 4, and 5. And so the derivative of y sub p would be, well, I need product rule for this first one, so that's going to be what? C3 e to the 3x plus 3c3 x e to the 3x. And then we're going to have minus c4 sine x. And plus c5 cosine x. And then y double prime is going to be 3c3 e to the 3x plus 3c3 e to the 3x plus 9c3 x e to the 3x minus c4 cosine x minus c5 sine x. So yeah, quite a lot here. We can do a little bit better. These two are the same terms. This is 3x. This would be 6c3 e to the 3x. All right, so remember this has to get plugged into the original differential equation, which was, what was it, y double prime minus 3y prime, and that should equal 8, what was it, 8e to the 3x plus 4 sine x, right? This is the original differential equation. So I need to plug the second derivative in and the first derivative in on the left-hand side. So all this that we found out here has to be plugged in. So just make sure you don't lose track of terms. It's not hard. You're just plugging yourself in. So 6c3 e to the 3x plus 9c3 x e to the 3x minus c4 cosine x minus c5 sine x. I'm going to run out of room here for sure. So what I'm going to start stacking things underneath common terms I'm going to bring together already. So it's minus 3 times the derivative. So if I multiply minus 3 times that, so minus 3 times this would be minus 3c3. So minus 3c3 e to the 3x, I'll stack it with that one. The next one would be minus 9c3 x e to the 3x. The next one would be positive 3c4 sine x. And finally, the last one would be minus 3c5 cosine x. And like I said, I stacked these so that I can group them already and combine them. And remember, this is supposed to be equal to your 8e to the 3x plus 4 sine x. All right, so what happens here? Well, clearly these two cancel. These would give me 3c3 e to the 3x. Here I would get negative c4 minus 3c5 cosine x. And the next one would give me 3c4 minus c5 sine x. Okay, so doing this equal parts idea here, here's the e to the 3x, this is the coefficient here, this is the coefficient on the other side, they have to equal each other. So if 3c3 has to equal 8, then c3 would be 8/3. All right, then we also have that this has to equal 0 because there's no cosine on the other side. So if negative c4 minus 3c5 has to equal 0, that tells me c4 equals negative 3c5. All right, and finally this right here would have to equal 4. So if 3c4 minus c5 has to equal 4, I know that c4 equals negative 3c5. This tells me that negative 9c5 minus c5 equals 4. So minus 10c5 equals 4. So c5 equals negative 4/10 or negative 2/5. Okay, and putting that back over here, c4 then equals negative 3 times that, so 6/5. All right, so we got our 3 values. Plug that in for y or y sub p. Combine that with your y sub c. And you got your solution. So finally, our solution would be that y equals c1 plus c2 e to the 3x plus 8/3 x e to the 3x plus 6/5 cosine x minus 2/5 sine x. So all that solve the non-homogeneous differential equation, which was y double prime minus 3y prime equals, what was it, 8 e to the 3x plus 4 sine x. Okay? And the nice thing is we're using Masonly algebra here. Like you notice we didn't do anything crazy with integration, nothing hard with any calculus-based things. It's largely just let's plug stuff in and use some algebra to satisfy these coefficients here. And that's what this annihilator approach is. All right, here we go. We got another one. Very similar to the last one in that I look at the left-hand side, linear, constant coefficients, right side, non-homogeneous, and we can annihilate that. D squared would annihilate the 5x. D plus 1 would annihilate e to the minus x, so the product would annihilate this whole sum. So we know we can annihilate it, so let's go with our first step, which is find y sub c. In which case it's y double prime plus 8y equals 0. So our auxiliary would be m squared plus 8 equals 0. And that would tell me that m, if I can get my pen to work, m squared equals negative 8. So m equals plus or minus the square root of negative 8. So that's going to give me m equals plus or minus 2 square root of 2 square root of 2i. Okay? And because 2 square root of 2 is how you simplify the square root of 8, you should be able to handle that. And there we go. All right, so that tells me now my solution for y sub c is two complex conjugates. In this case, alpha 0, beta is 2 root 2. So I'll get c1 cosine of 2 root 2x plus c2 sine 2 root 2x. So all that's my y sub c. All right, then we're going to go to y sub b. All right, in doing so, we know the annihilator, d squared times d plus 1. We know the original differential equation would be d squared plus 8. And we annihilate the right-hand side. Take a notice here. This is something you're going to have to get good at. Here's your annihilator. Here's your original equation. They don't share any roots if we were looking at the auxiliary equation. So, if they don't share any roots, we know we're going to pull out the y sub c. And if we're going to pull out the y sub c, then y sub p is only going to be created by using the new piece with, again, no repetition or anything to worry about with the original. And so I think we could jump to the fact that the m equals 0 times 2 and the m equals negative 1 are the new roots, and therefore that's going to form my y sub p. So my y sub p is going to be c3 e to the 0x plus c4x e to the 0x. I'm not going to write e to the 0x because that's going to be 1. And plus c5 e to the negative x. Again, that's all going to be the new piece. So there's your y sub p's form. Once you have the y sub p's form, we're going to have to take the derivative of it. So that's going to be c4 minus c5 e to the negative x. And the second derivative would be c5 e to the negative x. We're going to plug each one of those in to the original. We're going to do equal parts to figure out what the left side and right side equals so that we can satisfy the conditions for C3, C4, C5. Combine that with our y sub c, we got our answer. So again, the original differential equation was y double prime plus 8y equals 5x plus 2e to the negative x. We plug in what we got for the second derivative. The second derivative was c5e to the negative x plus 8 times the original, which was c3 plus c4x plus c5e to the negative x. And again, that should equal 5x plus 2e to the negative x. Distribute this 8 in here. Distribute this 8 in here, here, and here. Well, the only two things we can combine would be the e to the negative x's. So I'm going to have a c5 e to the negative x and an 8 c5. So basically I'm going to have 9 c5 e to the negative x plus 8 c3 plus 8 c4x. Again, matching it up with what's on the right-hand side, this would have to equal 2. This would have to equal 5. And this would have to equal 0 because there is no constant over here. So doing that, we figure out fairly easily that 9c5 equals 2. So c5 equals 2/9. If 8c3 equals 0, then c3 equals 0. And if 8c4 equals 5, then c4 equals 5/8. Okay? So, put that together, we got our y sub p. Remember, this is what y sub p was. So our solution should be y sub c, which was c1 cosine 2 root 2x plus c2 sine 2 root 2x, and then plus c3, but c3 is 0, so I'm not going to write that, plus 5/8, which is c4 times x, plus c5, which is 2/9 times e to the negative x. So there you go. That's the solution to this differential equation. The more of these you do, the quicker you get at it. You realize that it's very, very basic algebraic computation. As long as you keep track of your terms, shouldn't be a problem. And here we have a bigger one in that it's a third order linear on the left-hand side. And then we have this big piece we have to annihilate. But notice the instructions. Determine the form of the particular solution. So all we have to do is figure out what the form of y sub p is going to be, and then we stop. And so this is going to save us a heck of a lot of time. We're not going to find the full solution, but we'll at least know what the form of the solution should look like. All right, so let's think about annihilating first. This can be annihilated with a d cubed. This can be annihilated with a d minus 2 cubed. And this can be annihilated with a d minus 5. So the product of all those would annihilate the function on the right-hand side. If we look at first our step 1, which is find our y sub c, we would have y triple prime minus 4y double prime plus 4y prime equals 0. So m cubed minus 4m squared plus 4m equals 0. Factor out an m. You get m squared minus 4m plus 4, which we can factor even more, and m equal m times m minus 2 squared. So we get m equals 0 and m equals 2, and this one's repeated twice. So our y sub c would be c1 plus c2 e to the 2x plus c3x e to the 2x. All right, and we need that. We need that for y sub p, because we're going to pull that out of here. Now let's look at this. My annihilator is d cubed times d minus 2 cubed times d minus 5. This here, if I put it into operator notation and use the fact that I know I'm going to factor it out, I can write it as d times d minus 2 squared of y. Notice the repetition here with what we have here. So if we look at y sub p, we're going to get, for our auxiliary, m equals 0, but it's actually going to be times 4. The first one we've already used, and then the next 3 would be in y sub p. We're going to get an m equals 2, but that's going to be times 5. We've already used the first 2 in our y sub c, so the next 3 would be part of y sub p. And then we get m equals 5, and that's only going to occur once, and that's completely out of our y sub c. So if we put this all together and we form our y sub p, it's going to be long, so I'm putting it down here. It's going to be c4 x squared e to the 2x. Okay, I'm going to start here with these. I don't know why, I just felt like starting there. I already have the first two, which I'm going to pull out, so the next three are going to be part of my y sub p. So then c5 x cubed e to the 2x, c6 x to the 4th e to the 2x, so that takes care of the other three of these. Remember, I already used one of these in my y sub c, so the next three, which would be, what, c7x plus c8x squared plus c9x cubed. Again, because I have c1 already. For e to the 0x is what I'm doing for each one of those. And then finally, the last one would be c10 e to the 5x using this one. And so that's the form of our y sub p. And you can see that would be pretty ridiculous. We would have to take the derivative, second derivative, third derivative, plug all that into here to try and do the equal parts thing. And that would take forever. It's doable. I mean, it's just a matter of, do you have enough time on your hands to do it? This is not hard. I mean, you're going to do derivatives, product rule derivatives, basic Calc 1 derivatives. We could work it all out and find it. But the problem is then find the form of the particular solution. And this idea of remembering that when you have repetition from the y sub c into the y sub p, that's going to matter. Using the examples we've done so far, I think we can jump straight to here and realize that that is what y sub p should look like. And we would just then have to solve for all these pieces, okay, to find y sub p. So knowing when we should use this method is really important. All right, so this method using annihilators and undetermined coefficients, it's not applicable if we have variable coefficients, right? It only works if we have constant coefficients. The reason is all our annihilators, whether it's, d to the n or d minus alpha to the n, or even our d squared minus 2 alpha d plus alpha squared plus beta squared to the n, these are all our annihilators. They all have constant coefficients if you look at them. Constant coefficient here, constant coefficient here, this is a constant coefficient, this is a constant, this is a constant. These have constant coefficients. If you put those on top of something that also has constant coefficients, you stay with a constant coefficient equation. Whereas if we had variable coefficients, and now we're mixing in these annihilators, we have kind of a mixture of constant and variable coefficients, and we haven't even talked about anything like that yet. So it only applies if you have constant coefficients, and it only applies with constant coefficients where g of x is able to be annihilated. So if your g of x is like a log or 1 over x or tan or arcsine, we cannot use this because we don't know how to annihilate those functions. And so if I just gave you something like y double prime plus y equals log x, and we had to solve that differential equation, while it does have constant coefficients over here, since this can't be annihilated, we can't use this approach, which means we need another way. And so the next method we're going to learn is variation of parameters, which is a lot more useful for a multitude of different setups in our differential equation. And in the long run, variation of parameters would be used far more often than this would, but it is more involved, and so fairly integral heavy. So from a computational standpoint, it is more difficult. So that's why we learned this one first. If we can use this undetermined coefficients approach with annihilators, it's definitely going to be the easier way to go, but just know that you can't always use it.